Hi, welcome back. With this lecture, we start the second module in this course that is about HPC data structures and the HPC data layout and optimization. Today, I want to start describing probably the most important data structure for HPC, that is the array, that can have a different implementation in Python. So we're going to check the list and the tuples. Just in a brief introduction, then we will have specific lectures about this. And also we'll introduce the topic of memory allocation in Python. It is a topic that will allow us to understand how to get performance of the memory system within Python. We have two intended learning outcomes. So by the end of the lectures, we will be able to describe how Python lists and tuples, so-called arrays, are stored in memory. And also, you are going to be able to describe the implication of storing references for Python list, and you describe also what are the advantages and disadvantages of this approach. But let's start about the topic of arrays. So lists and tuples are a class of data structures that are called arrays. What is an array? An array is a flat list of data with some intrinsic ordering. Typically, with ordering, we have different indices, right? And these different index will introduce an order in our data structures. In Python, there are many ways to implement arrays, and each solution has its own useful features and guarantees. So we're going to look at what is the best data structure for arrays within HPC. In Python, there are two main types of arrays. The first one are called the list, and the second one are called the tuples. We're going also to talk about in this module about two additional implementation of arrays in Python. One is called array, not too much fantasy about this, and the other one probably already know, the NumPy array. That is a module. NumPy is a module for numerics. So let's go back to these initial array kinds. So what is the main difference between list and tuples? Well, the main difference is that the lists are dynamic arrays, so they can grow and shrink and allow us to modify the contents. Right? So we can take an element of our array, we can change it. And also, as I said, they are dynamic, so we can actually resize. So if we need to add more element to the array, we can actually do it. Differently, tuples are static arrays whose contents are fixed, so we cannot change. Once we initialize the tuples, we cannot change the values of these tuples. And immutable, so we'll throw an array if we try to change it. So let's look at how Python memory, the allocation is working, and what are the particular feature of Python in allocating memory. System memories on a computer can be thought as a series of a number of buckets. So you see here on the slides, we have different buckets, and each bucket is characterized by one number in hexadecimal format. So you see here 0x, that stands for the hexadecimal format. So we store our data on a series of buckets, each one with one index. What we have in these buckets? So the one surprise of Python that in this bucket we do not have actually the data that we want to store. What we have instead is a reference. You can think a reference as an address to a memory. So the number that we have in these buckets is a number that simply points or refers or address the data we actually care about. So results, the buckets can store any type of data that we want, because we are basically just giving a reference to the place, and you can at that reference we can have any type of data that we want. That also means that we have a list, and this system here we can have a list of different kinds. We are not forced to have only one kind for the reference. This we will see that is very different from NumPy arrays. We have a static type that can store only one type of data. So for instance, NumPy, we can have only an array of integer, an array of single, and we cannot mix kinds. So we saw that this architecture here of the memory system in Python allow us to have a mixed type within the same array. What happens when we want to create an array in memory? So when we want to create an array, such as a list or a tuples, we first have to allocate a block of system memory, where every section of this block will be used as an integer size pointer to the actual data. So we see that here for each bucket we will have a number that is an integer, specifically a long integer. We say 8 byte, and this will tell us where is the reference of the actual data we are referring to. When we allocate memory in Python, this involves a system kernel call to the OS, right? So we get out from our Python and then we call the OS. And what we do, we talk to the OS and requesting the use of n consecutive buckets, depending on how many array elements that we want. So this is the most important point probably of this lecture, is that to think about what are the implications whenever we allocate. So whenever we allocate in memory, we call the system kernel, we call the OS to reserve a certain amount of memory and consecutive buckets to our array. So the fact that we are involving the OS and we are making a system kernel, it has some performance implication. So whenever we do allocation, it has some time that is basically talking to the OS. So memory allocation are typically slow. So we will have a general rule of thumb. We want to have the least number of allocation to amortize the cost of going and talk to the OS. So let's just see a practical example of storing by reference in memory, and also how Python manage memory. So as I told you, lists and tuples are stored by reference. So if we want to know what is the size of a certain array, we can use the get size of a function that is in this module called import sys. So the module is called sys, and what we can do, we can import this module and access this get size of a function. If we take like an empty list, so just a bracket, we'll see that just a list with the 0 array elements will take 56 byte. If we put one integer, we get 64. If we have a list with the 2 integer, 72. With the 3 integer, we get 8. Also, you see that if we have a list with the 3 types, we still have the size of 80, regardless of the type. So in this case, we have integer. In case we have a single and double precision, but the size of this list is the same. Why is that? Well, the reason is because we are storing by reference, and reference is an integer number of 8 bytes. The most important things we need to understand is that the list doesn't contain the integer object itself. Instead, it contains 8 byte pointer to the actual int object. And the get size of function returns only the memory of the list and the pointers to the object, and not the actual data. So why we have this kind of architecture? Well, the motivation to have this architecture to store it by reference is due to the fact that this allow us to retrieve an element in rather fast way. The time to access one data into the memory is a constant, right? Regardless the size of our, because what we need to do, we just check which buckets and we get the data. Similarly, in some sense to hash map to retrieve data. So let's look at an example of this. In this case, I'm using IPython, and then I'm using the magic command, IPython magic, that is % time it, What I'm going to do is to create a list and then to retrieve an array, one element array, in this case the array with the index 5. I use here the double to get what is the timing for this particular part of the code. As you can see here, I time using a Python following the following operation. In the first case, I create a list with the 10 elements. In the second case, I create a list with the 10 millions elements. And then what I do an operation of accessing. In this case, I access the element 5. In this case, I access the element with index 100,000. You see that the performance is actually the same. So a bunch of execution have been executed. Then we take the average plus minus the standard deviation. You see the most important point that the access to the array element does not really depend on the array size, right? It's not 10 or 10 millions, but the time is basically the same. So it might look like a quite expensive way to store data in memory. To store some bunch of bytes just for the metadata, we saw that even with the empty list, we already have 56 bytes that have been used, right? And then we store 8 byte for each reference. So one of the possibility is actually one of the performance optimization that Python does is that whenever we start Python, it can pre-allocate some memory that we are very much likely to use. An example is the pre-allocation of a certain range of integers number whenever we start Python. In fact, Python virtual machine keeps a global list of all the integers in the range of -5 and 256. Why is that? Well, because it's very likely that we're going to use this number for indexing. So Python, what it does is pre-allocates. That also means that whenever we start the Python virtual machine, we are using basically 6 kilobyte, right? 266 elements, and we store this byte. Even if you're not going to use them, there might be a chance that we're not going to use it. We can verify that by using the ID function, ID parenthesis function in Python. It gives the pointer to the actual object. Right? So if we when we allocate, we get a pointer. If we allocate something different, part of the code, we might get a different pointer. If we use the ID function for checking, what is the reference for a certain integer, we will see, for instance, that when I do ID -3, we will get this number. If I later on I do again ID -3, I got the very same number. And the reason for that is because these integer number have been pre-allocated by the Python virtual machine. If I try to do the same trick, I do ID, but in this case, I take a number that is outside this range here. You see, I take a number here, and if I do later on, again, the very same command, I will get another number. Right? So a different reference. While these actually are pre-allocated because I'm using an index that is within the range -5 to 256. Few considerations about memory management in Python. Python virtual machine use quite a lot of memory for this object, but also it tries to employ various tricks and optimization for the management. By keeping track of the object memory usage and being aware of the cost and how memory is used in Python, we can actually also understand how to reduce the memory footprint or the implication of certain operation. So to reduce both the memory used for the computational overhead, given for instance from allocating operation, we can use also more specialized packages like NumPy or the standard library module array. So the final message that we have, especially for HPC consideration, is that a generic code using lists and tuples that allow us to be quite broad, for instance, we can have a mixed type, will be always much slower than code that is specifically designed to solve a particular problem. Right? So for instance, NumPy and Python array are designed more for HPC application. So we lose generality, but we will improve the performance. So this is the last slides of my lecture. To summarize, Python arrays are lists and tuples. We will see later on also arrays module and the NumPy module. System memory on a computer can be thought as a series of number of buckets. In Python, each of these buckets contains a reference. An important point that I want to make is that allocation of memory is always an expensive operation because it asks us to talk to the operating system. Right? Is a call to the kernel. We mentioned that the data in Python is stored in buckets by reference. In general, Python virtual machine used quite a lot of memory for its objects, such as lists and tuples, but is also trying to utilize various tricks and optimization for memory management. That is the last slides, and talk to you soon.